Hey there. Well, welcome to this video. We are going to talk about Arrow data structures, specifically the Arrow array in this one, and see how we can inspect it at runtime with a debugger and see the inner workings of the Arrow array. So if you were to actually look in the Arrow documentation and look at their specifications, they have the Arrow columnar formatted documented. So you can find a lot of information around like, okay, well, how is an integral array actually laid out in memory versus string versus binary, bit, whatever your type may be. So this is really cool. It's just updated with awesome visuals. I think it's a great starting point. But if you're like me, sometimes you just want to like dive in it and kind of see it firsthand and feel it a little bit more in the debugger. So let's take a look at a small sample program here to do that for us, which I'll post to GitHub for you to use on your own. We have a really simple main function down here where all we are going to do is build an integral array. We're going to build a string array, and that's it. I'm not printing it out. I'm not doing anything with it. These functions are pretty straightforward. The integer one's a little bit easier to start with, but you can see we're creating 32-bit integers in an array, and we're appending the values 0, 1, 2 in this loop, adding a null value, values 3 and 4, adding another null value, and then adding values 5 and 6. Okay, so I picked really easy numbers to work with. So as we look at this in memory, it's going to be a lot easier to kind of put your head around. The string array, build string array function we have does the same exact thing, except we're adding values like foobar baz instead of 0, 1, 2. Okay, so slightly different call signature with strings, but we're following the same builder pattern. We're instantiating this array with a certain type here, nano arrow type string, starting to append, actually doing the append and finishing things off to complete our array before we look at them. So let's just jump right into the project. I used Mason as the build system for this. Okay, so you're not tied to Mason. You can use CMake, or you could do this by hand in a simple project if you want to. I just like Mason. So I'm going to go ahead and set up my build directory for this. It'll take care of downloading Nano Arrow for me with the specification I have provided. Just real quick, I have my Nano Arrow dependency, and I want to create this debug arrow structures main executable. Okay, so that's nice and straightforward. I'm actually going to change my build directory, and I'll just go ahead and compile the program that I have set up. So everything there is nice and simple. I can run this program. It does nothing, it prints nothing, but it comes back, without any kind of error. Whoops. Right, so no failing return code there. Okay, so let's go ahead and fire up GDB as we attach to this executable, and I'm just going to set breakpoints on build string array, and I'll set another one on build int array. What am I doing here with my shortcuts? There we go, build int array. Okay, and I'll just run the program now, and we're going to stop right here first with build int array, which was the first function that we called. Okay, so I hit line 4. I could have also picked the lines that we wanted to go to. I'm not really interested in looking at the builder application. You can inspect that on your own. So I'm just going to go ahead and jump down to line 16, where we finish everything and go one beyond that. At this point, I have an array with that kind of structure. It's a struct arrow array. If I were to inspect this in the arrow source code, I would see the struct definition like no count, offset, buffers, children. Some of these are pretty straightforward, right? Length and no count. I think you can get a feel for. I can do print array null count, and it'll give me back the number 2, which is not surprising because I had 2 null calls as I was building this before I finished it. Array.length is going to give me back 9. I had 9 values in total. 0, 1, 2, 3, 4, 5, 6, and then 2 null values. So that's how I got there. Where I think you really get interested in inspecting this is when you look at the buffers. Okay, so this is something you'd have to really understand, start with the documentation on, because in C, these are just all a pointer to void pointers, an array of void pointers, essentially. So it's generic storage that you have to kind of just tie to the type that you're working with to understand what is actually contained within those buffers. But generally, most, if not all of the the arrow array types The first buffer is going to be holding a validity mask. Okay, so if I print this, it still comes back as void. I think they use int8 as storage, so I could do something here like, let's go ahead and cast this to int8 to see, what I'm looking at in more detail. But I think the easiest way to kind of look at this is to actually use the X command in GDB. So if you're not familiar with it, I always have to look at this myself too. X helps you examine memory and has this x/format address thing, right? So what I want to do here with this first one, which is the validity map, is I'm actually going to look at in binary view, which I think is the most helpful way to inspect this. I'm doing x-t, and I'm going to say array.buffers 0. And if you look at that and read the values, now this is the most significant bit comes first, right? So if you're thinking about like how we naturally read decimal numbers, the further left a number is, the more significant it is. So our smallest contributing values have it all the way here on the right. Because we're dealing with a validity bitmap, it can really only be in one of two states. You're either a valid record or you're not. So every time you have a valid record in Arrow, you get a 1. Every time you do not, you get a 0. So pay really close attention, start right to left, and look how I have 1, 1, 1 here. Well, that shouldn't be surprising because I appended 3 valid integers to start my array. Next, I have 0, meaning this is not a valid value. Well, that goes back to the first null I've provided. And then I have 2 more integer values, 1, 2 right there. 1 more null after that, which is there, and then 2 more valid values, 1, 1, which I see here. Now beyond that, beyond the number of bits that correspond with the array length, I actually don't know if they have to be all 0. It may be unspecified, but you're really only going to inspect the number of bits up to your array length anyway, which again in this case is 9. And you're reading that again from right to left, starting with the least significant bit to understand what is valid or not in your array. Now, the next buffer, because I know I'm dealing with an integer type, is my data buffer. So integers are primitive types. They're fixed in memory, pretty easy to work with compared to other data types. So I only need the validity map and the data itself in one buffer here. Again, it's a void pointer, but I can use help. I'll look at helpx again. I know I'm dealing with 32-bit integers here because that's what I said when I was building this. If you don't know, looking at the array itself, you should get a schema attached to the array, which aren't going to show here, but the schema will tell you, hey, I'm dealing with this type of data when you try to actually look at that storage. So 32-bit integer is going to be a word here, size-wise, and I'll go ahead and look at this, and I guess it really doesn't matter. I could pick decimal, will be fine, right? So I'm going to do x decimal for each word, and I'm going to look at my array. I also want to look at, we have a length of 9, so let's do 9 decimal words is what I want to look at, and that's starting with array buffers 1. So those are the exact values that I put into this array. 0, 1, 2 to start. Then I had a null value, so this really could be anything. It's 0 in this case. And then I have 3, 4 that I added here. Again, another null value or invalid value. That could be whatever. And then 5 and 6 after that. And I can see that through this examine memory tool exactly in that. Now, you don't have to look at this that way. You could look at it and, I don't know, I want to look at, let's do hex words or whatever, right? Or if I even just did, let's just do 8 hex bytes. You can kind of get a feel for that data and see it's the X tool just helps you kind of visualize it differently, whether you want to see it in octal, hex, decimal, binary. You have all those options, but the memory region is essentially the same. It's just giving us those numbers corresponding to what we started with. So let's move on. That was integers. We'll go to strings. Now there are way more types than just string and integer, so I can't go over all of them in this video, but just to give you a feel for a second type, and you can kind of refer to the documentation and learn how to debug and hopefully progress from here. I'm going to go down to line 45 in my code again, and I'll just finish this array. So once again, I have a array here. I can dereference that, and this will give me a view of, okay, the length, null count, number of buffers. Okay, so this time we actually have 3 buffers because our layout for string data is a little bit different. But let's jump right back into that again. So I'm going to go ahead and do X, and I'm going to look at a binary bit by bit view of the first buffer. So we'll go array buffer 0, and I get that same pattern that I saw before with the integral array. Again, reading this from right to left, 1 means it is a valid record, 0 means it's not. I'm actually going to skip ahead to the second buffer here and interpret this as a string. And what you'll see is all of the values that I had here kind of packed together, foobar, baz, cux, so on and so forth, right? So that's just how the string type works. Now there's string in Arrow, there's large string, there's string view, there's binary, there's all these different types. So this is very specifically the string type, a very specific physical implementation of a string. So be aware that there may be different types that you look at. But for this one, it packs all those sequences together. And what happens is this buffer in the middle ends up giving you kind of offsets into where each string should start and finish. So I know I have 10 records. I need to actually get an extra offset from this arrow array. So if my math is right, hopefully it is, I'm going to go ahead and pick 10 of these, and we'll pick decimal representation, and I'll do a word again because these are 32-bit values I'm dealing with. And this is the bounds for each of these values, right? So the very first record I added was foo. In buffers 1, it starts at record 0, going up to but not inclusive of 3, right? So this is 0, 1, 2, stop by the time I get to 3. Continue on 3 and 6, so that's 3, 4, 5. I stopped at 6. Okay, you see the pattern here. That's the next word going to 9. Right now, I see 9 here kind of repeated. Again, remember that 9 to 9, it's null value. I guess it just chose to repeat it. I don't know if it requires that to be the same number as the preceding one. This is our null value here, right? So after we did foobar baz, we added a null. That's why we see 9 kind of repeated. Continue on from there. I have 3 more letters from 9 to 12. And then after that, 12 to 16. 16 again was another null value. And then I finally see 16 to 21 and 21 stopping at 27. So that is a physical implementation of the string type inspected in GDB. All of the array types, again, they have different rules and specifications are all documented, but they generally follow the same pattern. Most of them have 2 or 3 fixed buffers. Okay, like string views get a little bit more complicated, but read the documentation and get comfortable with debugging this type of way, and you'll be able to basically work with any kind of Arrow data and understand at a deeper level how these memory layouts work and how they can achieve such high performance. So thanks for watching this video and hope you enjoyed. I'll see you the next time.